I'm Lori Leshin. I'm the president of the Planetary Sciences section of AGU. And on behalf of myself and Biogeosciences section president Jennifer Harden, I would like to welcome you to this year's Sagan lecture. As a joint endeavor between our two sections, this lecture embodies the interdisciplinary spirit of AGU. And of course, the lecture is named for Carl Sagan, a giant in the field of space science, and ever an optimist about the possibility of life in the universe. So this morning, in this lecture and the next lecture, which will be by Sean Solomon, which is our Shoemaker lecture, and I urge you to stick around for that. In these two lectures, we're actually exploring inner solar systems from two different perspectives. In fact, Sean's planet is the outermost planet, I think, in the discussions that will take place in the next 2 hours. So that's a unique position for him. So now I'm pleased to actually introduce our Sagan lecturer for this year, Dr. Geoff Marcy, professor of astronomy and director of the Center for Integrative Planetary Science at the University of California, Berkeley. As I'm sure most of you know, Geoff is a true pioneer in the very exciting field of exoplanet research. His group has developed groundbreaking techniques for detection of planets around other stars, and in fact has discovered 70 of the first 100 known exoplanets. He also discovered the first multiple planet system around a star similar to our own, the first transiting planet around another star, the first extrasolar planet orbiting beyond 5 AU, and the first Neptune-sized exoplanets. Geoff is a member of NASA's Kepler mission team, and we're actually grateful he's agreed to take a break from a very big Kepler science conference at NASA Ames to be with us today. He has many honors and accolades. I'll only mention a few. He's a member of the National Academy of Sciences and winner of their Henry Draper Medal. He is also a recipient of the very prestigious Shaw Prize. Like Carl Sagan, Geoff has a great gift for making space science accessible, exciting, and inspiring, and I'm sure he's going to spark all of our imaginations today with his Sagan lecture entitled Radii, Masses, well, actually, here it is, it's up here, Diameters, Masses, and Occurrences of Planets Nearly the Size of Earth. Get ready to have your mind blown. Geoff Marcy.
Well, what a pleasure to be here today. We are engaged in a revolution in planetary science with regard to exoplanets, and it's so fast-paced that I had to work on today's lecture with results literally from this week. So it made it a little more challenging, and I'm going to try to give you an overview of what we've learned about planets around other stars, especially the smallest ones we've found nearly the size of the Earth, and try to tell you about some of the most recent results. So, of course, one of the backdrops is the search for biology elsewhere in the universe, and as everybody knows, we are yet to find any evidence of biology outside the Earth. And of course, many people are interested in the prospects of intelligent life outside the Earth. And so the search for habitable planets is a major endeavor right now, and I'm going to try to tell you a little bit about how we do it. Here's the primary technique. We detect Earth-sized planets when they cross in front of their host star, blocking a little of the starlight, dimming the star. And so we can't detect the planets directly around other stars, but we can measure the brightness of those stars very precisely, allowing us to detect the repeated dimming orbit after orbit as planets cross in front of their stars. You can't do this from the ground because the Earth's atmosphere is like watching the heavens from the bottom of a swimming pool. So NASA very wisely built a telescope, put it at the top of a Delta II rocket, and launched it 2.5 years ago to make these kind of precise observations. And I hope I can run this movie. We all went to the Kennedy Space Center quite nervously. The sound isn't very loud, but that's all right. Yeah, that's okay. The sound doesn't matter. This was a moment when everybody on the Kepler team was sitting there either at Kennedy Space Center or on the beach. We were very nervous because the previous rocket that NASA had launched had failed to properly deploy its nose cone, so we were delighted to see this go up successfully. You can see the solid rocket boosters right here that are powering it. So we were absolutely beyond delighted. Most of us had tears running down our face and hairs standing up on the back of our neck as the Delta II rocket was successfully deploying the Kepler Telescope. And I'm now going to tell you a little about the telescope and then the results. So this is what's special about Kepler. It's a 1-meter diameter telescope. But it has a very wide field of view, 10 degrees by 10 degrees, 20 full moons by 20 full moons, a 95 megapixel camera at the back. It captures the light of 150,000 stars every snapshot, and it does so every 30 minutes. So we get a measure of the brightness of every one of the 150,000 stars every 30 minutes. And the mission has a nominal lifetime of almost 4 years. And what's exquisite about this particular telescope, making it superior to, say, Hubble and other spaceborne telescopes, is that it can measure the brightnesses of stars repeatedly to within a part in 10 to the 4. And that turns out to be crucial. Here's the field of view. It's in the constellation Cygnus. You can see it tonight. When you go out in the evening, you'll see Cygnus high in the west. We just stare at this field of view and the 150,000 stars there. Here's the field of view magnified. And I'll show you one of the stars that captured our attention early on, Kepler-10. It's just one of the 150,000 stars, and I thought I would show you a little animation of the field of view showing you where Kepler-10 is, mostly to give you a sense of how many stars in our Milky Way galaxy we are monitoring. So there's the patch. You see the separate CCD detectors, and you can see how many stars there are in each one of those CCDs. And we download postage stamps around each star, bring them back to NASA Ames, and then the NASA pipeline software engineers measure the brightness of each one of the stars, and Kepler-10 turned out to be interesting early on. And here's why. Here are the data for Kepler-10. Let me walk you through this. It's very simple. This is just the brightness of the star in units of its average brightness, 1. And then here's time. You're seeing about 200 days of Kepler photometry. And if you look carefully, you'll see what's extraordinary is the vertical scale of this graph. Here's the average brightness, but here's 0.9995. So the noise that you can see here by eye is only 1 part in 10,000, allowing us to detect Earth-sized planets because the cross-sectional area of the Earth is about 1/10,000th of the cross-sectional area of the Sun. So when the Earth crosses the Sun, it blocks only a part in 10,000, and that would be a 1 sigma detection, but then we get many such crossings. And so here you can see, if you look carefully, a dimming of this star, Kepler-10. There's another dimming, another one, another one, another one. So there's a repeated dimming of the star shown here, indicating the presence of a planet. The period of the orbit is 45 days. You can read it off with your eye. It's every 45 days the planet crosses the star and dims the star. And what's interesting, if you zoom into a little piece of the data in the green here, and if we zoom in there, here's the original plot. And if you zoom into the green section, that's this big plot, and you can see there's one of the dimmings we saw before, but there are now additional dimmings, the little ones. That's a second planet orbiting this star with a different orbital period. Now you're only seeing 10 days of data, and so these dimmings occur even more frequently than once a day, the period being 0.84 days. So this is a very close-in planet, smaller than the first planet, both of them orbiting the same star, Kepler-10. And there you can see all the dimmings laid out. We, of course, can immediately calculate the radius of the planet because we know the radius of the star fairly accurately from spectroscopy. We know its characterization quite well. And so here, the transit depth, as we call it, the dimming amount, 0.00015, tells you pi r squared of the planet divided by pi r squared of the star. It's that simple. So we can immediately deduce the radius of the planet, and it turns out to be only 40% larger than the Earth. This is, in fact, the smallest planet around a sun-like star ever discovered. We announced it a few months ago. The orbital period is ridiculously short, taking less than a day, but we have quite a few other planets in such short and compact orbits. Here's what it looks like. This graphic is to scale. You see the star, Kepler-10, you see the planet in silhouette, and then, of course, there's the orbit. It's impossible, of course, with planets in our solar system to show all the sizes to scale, but this is such a close-in planet that you can do so. NASA made a movie of this, which I'll show in a moment, but there's one other measurement I think is wonderful, and that is, yes, we can measure the radius of the planet, as mentioned, but we can also measure the mass of the planet by Doppler measurements. By watching the star spectroscopically, we can watch for the wobble of the star caused by the gravitational pull on the star by the planet, thereby giving us a measure of the mass of the planet. We do this with the Kepler Telescope in Hawaii on Mauna Kea, and here are the data, velocity of the star measured by the Doppler effect over the course of one orbital period, and you can see the velocities go up and down and up. It's a difficult measurement. The star is moving by only a few meters per second, human walking speed, and yet we can measure Doppler shifts that precisely to get the mass of the planet. It turns out to be 4.5 Earth masses. And now, of course, you can calculate the density of the planet. You have the mass, you have the radius, and the density turns out to be 8.8 grams per cubic centimeter. The Earth, of course, has a density of 5.5 grams per cubic centimeter. So this is a planet surely solid, by virtue of its density being even greater than that of the Earth. And indeed, because it's denser, it probably has a slightly greater admixture of iron and nickel, perhaps a larger iron-nickel core. Here's the artist rendering of Kepler-10 with the suggestion of a little more iron and nickel, so close to the star that one hemisphere is blowtorched to very high temperatures of about 2,000 degrees Celsius. The backside would be quite cold, no chance of an atmosphere. And then NASA, of course, predictably made a nice animation of this planet. And of course, being solid, it gave us an opportunity to try to imagine the plate tectonics, volcanism, the mineralogy on such a planet. And it's based on almost pure speculation, extrapolations from the terrestrial planets in our own solar system. But it gives us a sense as to what kinds of future measurements we might want to make of this rocky planet. NASA included some white flecks there in the sky for reasons I have no idea. And then here's the imaginary surface of the planet. Again, at 2,000 degrees Celsius, some of the rocks would be very close to their melting points. It's not clear whether there'd be liquid lava on the surface. You can see the animators watched Star Wars too much. But it's a remarkable era. It was only 16 years ago that we had not discovered any planets around other stars at all. So in 16 years, we've come from just hoping that someday we might find extrasolar planets to now finding rocky ones with well-defined sizes and orbits, and maybe even some sense of their chemical composition. We've found many other planets now, 2,000 planets with the Kepler spaceborne telescope. This is Kepler-4. You see the repeated dimmings above. There's the folded light curve, as we call it. You can read the radius of the planet off by eye. It's 4 Earth radii. Many of the planets, oops, let's see if I can go backwards. Yeah. The majority of the planets Kepler is finding have very small radii compared to Jupiter anyway, 2 to 3 Earth radii. You can see how easily planets of just a couple times the radius of the Earth stand out in Kepler data. And the real take-home message of this slide is if you can find planets of 2 to 3 Earth radii easily, surely you can find planets of 1 Earth radius with just a few more orbits building up the signal-to-noise ratio. And that's, in fact, the main goal of Kepler, finding Earths in the habitable zones around Sun-like stars. In February, we announced about 1,235 planets. And this is a two-dimensional plot which I'll introduce you to. I'll show a few of them. This is the size of the planet on the vertical axis in units of Earth diameter. So here's the Earth at 1, 4 Earth radii, 10 Earth radii. And then on the horizontal axis is the orbital period, 1 day, 4 days, 10 days, 40 days, 100 days. And you can see something we never imagined before Kepler launched. This enormous swath of planets that have sizes between 1 and 4 Earth radii, 4 Earth radii being the size of Neptune, and orbital periods quite short, weeks or months. So around normal stars in our Milky Way galaxy, there are a fantastic number of planets the size of Earth up to Neptune. There are, of course, some Saturns and even some Jupiters, about 10 times the size of the Earth. But the dominant planet that we're finding are these 1 or 2 or 3 times the size of the Earth. And of course, as the duration of the Kepler mission lengthens out to several years, we will be able to find the planets that have orbital periods of a year or 2 years. We just haven't had quite enough time to do so. And the probability, the geometrical probability of a transit of a planet being so edge-on in its orbit is smaller and smaller. So one has to do some statistics here properly to understand the occurrence of planets. Luckily, we're finding more of them. And just 3 days ago, on Monday, we announced another 1,000 planets. And so here's the slide of the additional 1,000 planets shown in yellow. So you can see that with Kepler, we're finding smaller planets now under an Earth radius, smaller than the Earth, some of them half the size of the Earth, and longer orbital periods. So Kepler is just a gold mine in the process of being dug out, and we're going to find small planets under the size of the Earth and planets out at Earth-like orbits. You can correct for these geometrical effects, and this is the histogram of planet radii. Here's 1 Earth radius, 2, 4, 10, here's the size of Jupiter. And in this histogram, the take-home message is that something like 10% of the stars have planets in this range of, say, 2 to 3 Earth radii, an extraordinarily large number of stars, 10% of them, in close, with orbital periods less than 50 days, have these small mini Neptune sizes. And in contrast, the Jupiter-sized planets, they're out there, but they're rarer, and maybe understandably, because they're the largest of the planets. So it's these large Jupiter-sized ones, they occur, but with an occurrence rate of only about 1% around these sun-like stars that we're monitoring. And I think it's worth remembering for those of you who have studied the formation of our solar system, the two most puzzling planets, I would say, in our solar system are Uranus and Neptune. They have rocky cores, but only a small amount of gas. They obviously gravitationally acquired gas, but only a small amount relative to the gas acquired by Jupiter and Saturn. How could it be that our own Uranus and Neptune somehow acquired a small amount, but not a large amount as Jupiter and Saturn did? And now what we're seeing is that if Uranus and Neptune are puzzling to us, we now have a whole galaxy filled of such planets. This peak in the histogram at 2 to 3 Earth radii is an extraordinary reminder that we really don't understand planet formation very well. And so this is a big puzzle as to try to answer how our own Uranus and Neptune formed, not as exceptions to the rule, but as the rule. You can plot the planets Kepler has found on a diagram of their size, radius. Again, this is Earth size. In fact, there is the Earth, twice the size of the Earth, 4 times the size of the Earth, versus their mass, because we do have these Doppler and other means, dynamical means of measuring the masses of the planets found by Kepler. And so you're seeing here actually an unprecedented plot. I can tell you that this plot really essentially did not exist until about the beginning of this week. We added another 6 points to this plot just on Monday. And you can see the Earth is here, Uranus and Neptune are over here. One takeaway message are all of these planets. Oops, I need to go back, I think. Oh, I should point out before I mention the data, the theory. You see a solid line here that represents the locus of points of the masses and the radii for planets with the composition of the Earth, but larger than the Earth. Here's what they would do. And what's really extraordinary is how this curve turns over. It turns over, of course, because if you imagine spooning onto our Earth more and more material, the pressure increases on the core. The equation of state is such that the Earth would compress. And so planets don't get much larger than about 2 Earth radii if they're solid, if they're made out of Earth-like materials. And yet look at all these planets we're finding with larger radii. The take-home message being these are surely planets not solid. They have a component that is water and or gas, fluffing them out like Uranus and Neptune. We do, of course, have a few planets that are apparently solid, like this Kepler-10. The Europeans found Corot-7. We now have 321 that looks to be solid, a couple of others. But there are quite a few planets as well that are about the same mass, a few Earth masses, but have large amounts of water and or gas fluffing them out. So it's the sort of archaeology of this domain here of a few Earth masses that we need to concentrate on in the next few years. Are Earth mass planets typically solid, or are some of them composed of rock, water, and gas? So this is a major question, I think, in planetary science now. How do you form planets that indeed have these extra components, not just rock? So that's where Kepler stands with regard to individual planets, but it turns out Kepler is finding a lot of stars that have multiple planets, more than one planet, orbiting and indeed transiting in front of the star. And the poster child is Kepler-11. You see here the brightness of the star over the course of about 100 days, and you see this odd set of dimmings of the star. That's because this star has 6 planets that orbit in front of it, and I can sort of walk you through it a little bit. The blue arrows show the repeated dimmings from one of the planets. The yellow arrows show the repeated dimmings from a different planet. Here's red, planet C we call it. You can see repeated dimmings in the red arrows. And then I'll just show the other 3 planets all in one fell swoop. There are literally 6 different periodicities in the brightness of the star caused by the 6 planets. They're obviously in a coplanar geometry. The planets must reside in a flattened plane like the ecliptic plane of the solar system, giving us these dimmings. If they were tilted or inclined to their respective orbital planes, they wouldn't transit. In addition to the 6 planets that repeatedly dim this star, Kepler-11, you can time when the dimmings occur. That is to say, you can measure to within a minute when the star dimmed, and it turns out that these planets don't dim at regular intervals. That is to say, the planets don't cross in front of the star at regular intervals. Instead, sometimes the planet arrives a little early and other times a little late. And these transit timing variations are due to the gravitational interactions between the planets. One planet yanking on its neighbor, pulling it back or forward so that they move a little more quickly or slowly compared to their average speed. And we're using these gravitational interactions to measure the masses of the planets. Some of these multi-planet systems don't require Doppler measurements. We can just use the timing of the planet transits to determine their gravitational masses. Here's what the Kepler-11 system looks like. Quite exquisite. Coplanar, 6 planets. One of them is outward quite a ways. There it is. And there's a face-on view. We're finding enormous numbers of multi-planet systems. We now have 400 stars found with Kepler that have 2 planets or more. And this is, again, the poster child with 6. Here are all of them. You're seeing all the systems with 2 planets, here, 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 and here, the doubles. Here are stars Kepler has found with 3 transiting planets, 4 transiting planets, and some with 5 and 6. So there's an absolute avalanche of planets that Kepler is providing the planetary science community with, all ripe for study. You can actually take spectra of these stars, time the transits, measure the chemical compositions of the stars and their neighbors and so on to understand how that correlates with the planets themselves. And of course, in addition, we know the ephemeris of the planet orbits. We know what their orbital periods are, all of the planets, and we know when they transit the star. So they're each like clocks. We know where the planets are this very instant. Right here in this lecture hall, we can calculate where each of the planets are around in their orbits, and the next slide shows that. There's actual time ticking by here. That's literally the barycentric Julian date, and these are the literal positions of each of the planets. And I'm only showing about 170 of Kepler's multi-planet systems out of the 400. So you can imagine we are utterly overwhelmed, a relatively small science team, trying to characterize, archive, and study each of these systems. One of them that's most remarkable is Kepler-16. And I'm going to tell you the answer in advance because if I didn't tell you the answer, showing you the data would be just a little too confusing. We just published this in September, so 2 months ago. What we believe is happening here in this system is that there are 2 stars, star A and star B, Kepler-16A and B, a star a little smaller than the Sun and then much smaller than the Sun, a so-called K and M type star. And then we believe there's a planet orbiting both stars, a circumbinary star planet. Never before definitively found. Now let me show you the data and you can judge for yourself. What you're seeing here is the brightness of the star over the course of time, several hundred days, and you see the repeated dimmings by eye, even from the back of the room. That's because these 2 stars eclipse each other. They're in a flattened plane in our line of sight. Every time the smaller star crosses in front of the larger star, you get a nice big eclipse. So those eclipses are shown here. That's what one of them looks like. And there's the cartoon showing the smaller star in front of the larger star. A typical eclipsing binary. This is in and of itself not extraordinary. But in addition, if you look carefully, you'll see some other dimmings at smaller levels. There's one, and it repeats at a few other places. And notice this dimming has a flat bottom. The reason for that is that this is what happens when the smaller star goes behind the bigger star. And of course, the smaller star stays a long time behind the bigger star because it's dwarfed by the bigger star, and that means that the total light from the whole system stays constant for a little while as the little star passes behind the bigger star. And this happens every single orbit as well, and so there's quite a number of them. And then if you look even more carefully, there's some oddball cases. Here's a dimming. It's not flat-bottomed. What is this thing? Well, this is what happens when the planet crosses in front of the primary star, the larger of the two stars. There's the planet crossing in front. You get a nice, beautiful look at the signal to noise. Unmistakably, the planet, this is just the U-shaped transit light curve that we always see with Jupiters crossing in front of their stars. So there's a bunch of those. There's three it's shown here, but we have others. And of course, understandably, the planet crosses in front of those two stars on a regular basis as it orbits the two stars. But what's curious is that the timing is not equal. That is to say, I'll go back. You might think that the planet would cross in front of the primary star with equal intervals of time, but that's not quite true. The first one was a 230-day interval. The next one was 221 days, not quite equal. What's going on there? Well, naively, you might think, here's your primary star A, there's your planet. When they line up, we see a transit, we see a dimming. So that would be fine, except for the fact that's not the way it works, right? Star A and star B orbit each other around a common center of mass. And so the planet only lines up with star A wherever it happens to be in its little orbit. And then that causes a transit. But sometime later, the planet might line up with star A when it's at a different place in its orbit. And so the timings between successive transits of the planet in front of star A will be a little bit off, depending on where A happens to be in its little orbit around star B. So that's extraordinary, but there's one last aspect to this system. Every once in a while, and you can see them very faintly, there's yet a fourth type of dimming. That's the dimming that occurs when the planet crosses in front of the smaller of the two stars. And there's the cartoon, the planet crossing in front of the smaller of the two stars. We get repeated dimmings. There's three of them here. Again, we have others in the later data. There they are, 1, 2, and 3. And so the whole system is nailed down. This is the first definitive circumbinary planet. You see star A, star B, and then the planet depicted here. The news media had a field day with this, reminiscent of a certain Star Wars planet. And then finally, in my talk today, I'd like to tell you about a discovery we just announced this week that's fairly exciting. This is Kepler-22. You see the brightness of the star. These are raw data, and you can see the heroic act being carried out by the NASA software engineers at NASA Ames. They take what is quite ratty-looking brightness data and turn it into this with sufficient calibration. And for Kepler-22, you see there was a dimming early on, and then 289 days later, another dimming, and then 289 days later again, yet another dimming. And what's extraordinary, if you're thinking about these numbers, is you haven't heard me mention orbital periods quite this long. It's difficult for Kepler. It's only been up for 2 years. To find a planet that has an orbital period of roughly a year. And you see we got lucky. This transit occurred just after the spacecraft turned on. This transit occurred just before the spacecraft went into a safe mode. So we were lucky to get these 3 dimmings. Here's what they look like phased up. It's a very nice looking planet. It's very small. You can see 0.9995 down there. So this is a planet something like twice the size of the Earth, similar to some of the other cases you've seen me present. But what's extraordinary is the orbital period. At 289 days around a nearly sun-like star, this is an orbital period reminiscent of, well, the Earth and Venus. It's somewhere in between. And here's the civil engineer's sketch of the system. There's Kepler-22, the sun-like star, and then the orbit of Kepler-22b, as we call it. And then for reference, our solar system with the Sun, Mercury, Venus, Earth, Mars, and shown to scale. The green represents the so-called habitable zone, where water would be between 0 and 100 Celsius, i.e. liquid, if there were any on the surface. This planet, Kepler-22, was highlighted in the news media as an extraordinary discovery. It does reside in its star's habitable zone, as you can see, 289 days, making it just a little more illumination than the Earth gets. But I think the news media overplayed it some, because at 2.4 Earth radii, that's the size of this new planet. At 2.4 Earth radii, you remember what I said earlier, such planets cannot be solid. You can't have a solid planet that big. You can add all the mass you want to the Earth, and it would just compress down and never get up to 2.4. So this is a planet for sure, I would argue, has some water and or hydrogen and helium gas, making it more of a mini Neptune than a super Earth. And for that reason, I'm a little worried that the news media played up this as a prospective Earth-like planet. I think it has very little chance that there's a solid surface where water could puddle into lakes and oceans, making it suitable for biology as we know it, except there is an ocean, so there's always some chance, or there may be a liquid ocean, there's a chance that there could be some biology there. But the solid surface is way deep down to give it the density that this planet surely has. Here's the rendering of it. And again, I'm emphasizing that I'd argue it's more Neptune-like than Earth-like. So we are still in search of a planet with the Kepler mission that is definitively rocky and in the habitable zone. We have not found any such examples yet, but it's not for any reason that has to do with nature. We need to wait 3 years to see 3 full transits of a planet in a 1-year period. So I'll finish by saying that I think the most extraordinary result from Kepler are these planets of a few times the size of the Earth, even below the size of the Earth. Some of them for sure are solid, as you saw. And the multi-planet systems are common, many of them coplanar. So our own solar system is just one of billions within our Milky Way galaxy. And then Kepler-22b is the smallest exoplanet we've found so far in the habitable zone. And while it's not, while the planet isn't solid, I think the discovery is, and it's an exciting system in and of itself. So I think I'll stop there. Thanks. Shall I pick people out?
Yeah, please.
Go right ahead. It does. It's extraordinary that something like 20% of solar-type stars have Neptune-sized planets orbiting, to re-emphasize, very close in, with orbital periods less than 50 days. I have almost no doubt that between 50 days and 100 days, there are probably plenty of Neptunes there as well. So these planets with rock, ice, probably some gas, are sort of littering their respective solar systems, I would say. I mean, that's the almost certain message. Planets with some rock and some volatiles are very common. Yeah, go ahead. Yeah. Yeah, I mean, you've raised 2 very key physical processes that are playing a central role in the theorists' efforts. One is migration, these planets that appear to be Neptune-like presumably formed where there was water in a condensed form so it could stick together. That would put it outside, as you say, the ice line at sort of 1.5 or 2 AUs. And then the question would be, as you're suggesting, how did the planets get close in from where they formed farther out? And, you know, honestly, my view is that the mechanisms, and there are many of them proposed, by which migration occurs, the dominant mechanisms have not been identified yet. It could be that the planets interact with the gas while there's still gas, but I think even more likely, this is my take on the literature and reading the theoretical papers, that it's planets interacting with each other and a kind of dynamical friction that might play as large or larger a role in the migration of the water-laden planets, moving them around. Yeah. It's because God is looking down from above. If he were looking from below, it would be clockwise. I actually hadn't thought of that, but I guess the NASA animators like to make the planets go around counterclockwise. To be clear, we have no idea which direction. We can't tell if the angular momentum vector is, quote, up or quote down in some coordinate system. So we don't know which direction the planets are orbiting. Yeah. So the question, to repeat it, is, are the orbits circular or elliptical? And from Kepler, we barely can tell. And let me be just a little more blunt about it. Kepler doesn't offer that kind of information about the shapes of the orbits. But from the Doppler measurements, we can tell the orbits. And the bottom line is something like 80 or 85% of the planets are in quite elliptical orbits. And the remaining ones, 15% or so, are in nearly circular orbits, not unlike those in our solar system. For the multiple planet systems, where there's 3, 4, 5, or 6 planets, those orbits we've found tend to be more circular, understandably, because if they were in elliptical orbits, the system would be gravitationally unstable to the mutual gravitational interactions. So the multi-planet systems are typically more circular orbits, and then the stars that have only 1 or 2 planets have more wildly eccentric orbits. Yeah. The what last thing you said? Between the star and the planet. Oh, supermoon. I'm not sure exactly what you're asking. A lot of different things in my mind. First of all, yeah. It would, yeah. So there are a lot of exciting aspects to your points there. If the planets Kepler is discovering had massive moons, let's say a 3 Earth radius planet with a 1 Earth radius moon, for assumed densities, we would see the transit timing variations caused by those two bodies orbiting a common center of mass. The times of transits would be kind of chaotic, actually, from our vantage point. And so we would detect them. There are people on the Kepler science team looking, and so far we haven't seen evidence of moons either from the transit timing variations or from the extra dimming that you would see when the moon crosses the star as well as the planet. So we're looking, but so far no moons. And rings as well. We haven't found rings yet. Yeah. Yeah, I'll repeat the question. Do we throw out active stars? Many sun-like stars are young, have strong magnetic fields, and they have therefore flares and sunspots, and that changes the brightness in ways that actually, of course, compromises the planet detection capability by Kepler. So the bottom line is each star out of the 150,000 has noise, intrinsic stellar noise. And the youngest of the stars, the more magnetic stars with their spots and flares, are frankly not amenable to the detection of Earth-like planets. We don't throw them out. The data come down. There are many people excited like mad at these noisy stars because they're studying the spots and the flares and the magnetic fields and the dynamos and so on. But for planet detection, the young active stars are awful. Yeah. Yes. Yeah, exactly right. We assume, and it's a very good assumption, that the tilts, the inclinations of the orbital planes are random in space. And when you take that assumption, you can then, of course, correct for the planets we don't see, the ones that are in orbits so tilted that Kepler didn't see a transit. It's very easy to do the calculation. And then you can boost up, if you will, boost the number of planets we see by all the planets we don't see to get the total number of planets. Don? Yeah. Oh, I'll repeat the question. He's asking what's my take on the retrograde orbits. There's some spectacular evidence, the nature of which I won't bring up, that there are planetary systems in which the star is spinning on its axis one way with its angular momentum vector in some direction, but the planets go around the other direction. Very clear evidence, and something like 30 or 40% of all planets orbiting close in are in misaligned orbits, orbits very tilted or even retrograde relative to the spin of the star. And my quick take on it is, as I had alluded earlier, it's these planet-planet interactions that are playing a stronger role than we had thought previously. Planets form in multi-planet systems, they interact with each other, the system goes chaotic, and you end up with orbits that are in much crazier tilts and elongations than they had in the protoplanetary disk from which they formed. And so occasionally you end up with orbits that have nothing to do with their original angular momenta. How are we doing for time? Okay. Yeah, go ahead. Yeah, I think I understood the question. How much can the tilt be and the planet still transit the star? So two interesting answers to that question. First, it depends on how far the planet is from its star. A planet that is at an Earth-like distance from its host star, 1 AU, there's only 0.5% probability that it is so aligned. So Earth-like planets in Earth-like orbits, we only detect 1 out of 200 of them. Easy to calculate. By the way, the equation is simple. It's the radius of the star divided by the orbital distance. R over A is the probability that a planet will be so edge-on in its orbit that it will transit. And the corollary to your question, which I can't help but tell you, is that in our solar system, we normally think of the ecliptic plane in which the planets reside as a very flattened plane. But if you viewed our solar system from an extraterrestrial Kepler telescope out there 30 light years away, and you viewed our solar system, even if one of the planets did transit the sun, let's say Mars, the other planets would not. So our solar system, with its supposedly flattened plane, is not so flattened that you would actually see all 8 major planets cross in front of the sun. Instead, only one would. So even a few degrees, to answer your question directly, even a few degrees tilt is enough to prevent the planets from being detected by Kepler. Yeah. Absolutely, and we've found one already. So we time the transits of the planet that does transit, and then by the transit timing variations, we detect other planets. And of course also with Doppler measurements. So Kepler finds a planet, we look with the Keck telescope to try to determine the mass of that planet, and we find that there are other planets that are obviously non-transiting, and we call them non-transiting planets. We add them into the inventory, the family portrait around the star. Yeah.
What is your most distant Neptune object?
With Kepler right now having been up for only 2 years, it can only detect planets with orbital periods less than about a year or so, because we have to see at least 2 transits to even know what the orbital period is. So really, as you saw in the diagrams, we can only detect with Kepler periods of a year, but that's the goal of the upcoming this upcoming season in 2012. We're writing a proposal to NASA headquarters hoping for an extension on the Kepler missions, indeed, precisely to detect planets that are orbiting at 1.5 AUs and 1.8 AUs and so on, which would be lovely because that's still in the habitable zone. Yeah. What is the... Oh, the status. So I'm actually in charge of that program. We have Doppler measurements for about 30 of the Kepler planets right now. Good Doppler measurements from the Keck Telescope, run by NASA, in fact, and other institutions on the Big Island of Hawaii. So those radial velocity measurements, Doppler measurements, give us the masses and in some cases upper limits on the masses, which is also quite interesting. If you can say that a planet, is 2 Earth radii, but the mass is less than, say, 5 Earth masses, that tells you how low the density is of the planet, making it full of volatiles rather than solid. Yeah. Well, we actually don't. I'll repeat the question. When do we close out a star? Is that what you're saying? Yeah, and with Kepler, we don't do that. And we've thought very deeply about what is the right approach. We keep Kepler pointed at the same part of the sky all the time. They're in the constellation Cygnus. And so even when we find 1 or 2 transiting planets with Kepler around a particular star, we continue to take data on that star. And it's remarkable, quite often we find a 3rd or 4th planet that's very small by building up the signal-to-noise ratio by virtue of continuing to acquire photometry.
How much has all this cost?
$600 million.
But worth so much more.
Yeah.
All right, well, listen. So thank you again for a very stimulating talk. I would like to present to you, on behalf of the Planetary Sciences and Biogeosciences section of AGU, a certificate of appreciation for being our Sagan lecturer this year. Let's thank Jeff again for a great talk.
Thank you so much.
Actually, it's been another city.
Okay. Okay, thank you.